Hello, my name is Donald. I'm going to be going over resistivity for semiconductor materials. I really wanted to go and make this video because I think semiconductors are cool. I like the material covered in Dieter Schroeder, which is the book I'm going to be going over, specifically the first chapter, and it goes over 4-point probe measurements as well as measurements for resistivity and what to take into account when looking at 4-point probes. The rest of the book is also amazing. I highly recommend. Okay, so I made this video because, well, I think the information is important. Let's say you're working in a clean room or you're working with people who work in a clean room and you need to take some measurements in an iconic analytical bay, as we can see here. And you're given a wafer, and now you need to see the resistivity for the device or just the material itself. That's what this video covers and what to take into account when using a 4-point probe. 2-point probe and 4-point probe. What are the differences? 2-point probe is a little bit more difficult to interpret. This is because both contacts include a current and a voltage, while the 4-point probe includes separate voltages and currents, which we'll talk about. And the reason why it's separate is because it's a little bit more difficult to set up. The benefit of that difficulty to set up is no parasitic voltage within the resistance of the wire and resistance of the contact. And when I mean no, of course, some will exist, but it'll be a lot lower than other types of measurements or other measurements where the probes are a little bit more difficult or damaged. Now, 2-point probe versus 4-point probe. On the left-hand side, we have two leads, and those leads contain the voltage and the current in parallel. Resistance of the wire right here is also it also exists, while the resistance of the contact for the device under test, that's what DUT stands for, is also right here. Now, the resistance is equal to the voltage of the total voltage over the total current, which is equal to 2 times the resistance of the wire plus 2 times the resistance of the contact plus the resistance of the DUT, right? And we care about the resistance of the DUT, or the DUT. And with all this extra resistance, how do we get that? Well, that's why we would use a 4-point probe. Two separate leads exist, with the current also having some resistance in the wire and some resistance in the contact. Same thing with the voltage. And it gets us closer to just getting the resistance of the device under test, the device we care about, or the material or the wafer. That's why we would use a 4-point probe. And we would use a 4-point probe because we want to find the resistivity of this material. What does the resistivity hold for us? Well, it holds some unknowns that we care about for the material. So the concentration of electron, its respective mobility, as well as the concentration of holes and its respective mobility. So if we have the resistance, that's one less thing we could find, and we could try to find the concentration, the mobility of this material. Now, before we could go all the way to 4-point probe or even 2-point probe, we have to start at 1 probe. And this is what we're given for 1 probe. We're given the current that exists within the probe and the area that it is able to measure. And that area that it's able to measure is 2 pi r squared. Now, breaking some other equations down and using that to find what we want, we have the electric field right here, and that's equal to the current density times the resistivity, and that is equal to, sorry, I just sat down, that is equal to the negative change in voltage over the change in resistance. Now, the current density could be broken down by current over 2 pi r squared, and that could be replaced here, and I show that on the right-hand side where all of that is placed in the equation right here. Now, we set all of that still equal to negative change in voltage over the change in that space, that range, and we place the change in range on both sides. On top of that, let's see what happens when we take the integral of that. Taking the integral of that on both sides, meaning that with respect to r, we integrate that r, and we get 1 over r, just 1 over r right here. So doing some integration that's shown, the work is shown right here on how we integrate, that is placed right here. And we integrate the voltage, that just gives us the voltage, and it's negative. Both sides are negative right here, so the negative voltage, this negative right here is also taken away because both sides are negative. So now, for one probe, we know the voltage and what it's equal to and the resistance we're able to find. Moving on to 2-point probe. So if we have the voltage for one probe, what do we do for 2-point probes? Well, let's say we have this 2-point probe, and it has this range of distance that it's measuring and this range of distance that it's measuring. That's what changes the equation. So the voltage is equal to, similar to the equation we initially got, but the range of the first probe and the range of the second probe in the next part of the term. So this might, they're subtracting each other, as you can see. Taking out the common factor to make life a little bit more easier on us when we do some calculations, we could take out what we believe are constants and the ranges that we care about right here. Okay, so now we could just skip 3-point probe and go to 4-point probe. So we have the spacing 1, which is in between probes 1 and 2, spacing 2, which is in between 2 and 3, and spacing 3, which is in between 3 and 4. V2 and V3 are the measurements we care about for the voltage, and we talk about that in the following slide. So 2 and 3. So this is supposed to be 3 right here. It's a little bit sloppy, but it's also a 3. So the voltage right here for the second probe, we took out the common factor, and based off the spacing, this is what we have on the right-hand side. The book goes in a little bit more detail about it, but this is what we're going to be starting from. So V2 and V3, the spacing is separated like so. And if we want the total voltage, we're going to subtract V2 minus V3. So we're going to subtract this whole term by this whole term. Okay, so we're going to do that right here. So shown in the middle, we took out the constant term already. So we subtracted those two, and then I took out what we believe are going to be treated as constants. And then the spacing between each probe is kept below, and the proper algebra was done to get this equation in the middle. Now we're going to do some more algebra so that we can get the resistivity, because that's what we care about. We care about the resistivity. So doing some more algebra, we're able to move the resistivity over here, the total voltage over here, and then rearranging some of the constants and the current to look a little bit more appropriate and look a little bit more nicer to the eye. So here's the cool thing about this equation. So if we got where we came from before, and we did more algebra by setting all the spacing equal to each other, because let's be real, they're going to be pretty equal to each other if you're using a standard machine in an analytical bay. If you're using something from a shop or some first party instrument, you're going to be able to just set it all equal to the same spacing, and we get 2 pi times the spacing of all the probes times the voltage over the current, right? And we're doing voltage over current measurements when we're doing resistivity. So that means our calculations just got a whole lot easier if we're just given voltage and current from what we're looking at, and looking at probably our manuals or our data sheets for the device that we're using or the instrument that we're using. We could find out the spacing. You could even measure it yourself, and you could get the resistivity. So we got the resistivity, but just like everything in the real world, it's the real world, so we have to take in some correction factors, and these correction factors exist in many different forms, and we're going to go over that real soon. But before we get over that, we need to understand why we're going to go over that. What are things that we should keep in mind? What kind of measurements would this account for? Because if we're doing some kind of product that's already out there, then then maybe we don't need to do this too much. But if we're doing something we made ourselves in a lab, we're gonna have to do a little bit of testing and taking care of some of those extra factors that may exist. So like I said, that is really cool, but why do we care about these factors? Why do we care about putting in this extra factor? And like I said, it's a lot of that is because we care about finding out the truest form of this resistivity measurement. Okay, weird samples. So not all of us are perfect. I know I'm not, and neither is this wafer right here. So there are rules on finding out what the resistivity is on these materials and on the shapes of certain materials. And we have to do measurements in a specific way. Okay, here are the rules from the textbook, which cites another location. The contacts are at the circumference of the sample, meaning they're near the edge. Okay. Number two, the contacts are small enough, meaning that they're pretty thin, and we need to, or we don't need to worry about a lot of the extra resistance that the contact may bring. The sample is uniformly thick, so if the sample looks something like this, right? Like this goofy looking thing, the depth that goes into the screen or out of the screen, whatever direction you want to go, has to be the same across the entire sample. And we'll show that real soon. And no isolated holes and is completely whole. So that means that there can't be just a random hole in your wafer, and it has to be complete, meaning you can't just take measurements off of like maybe a broken sample, right? That's too weird. That's too weird, and we're gonna bring that up. We'll show a couple of drawings I've made that are very similar to the ones in the book. Okay, all are this thick, meaning they all have the same depth. So if this was a cross section of this material, let's say it's silicon, they all have to be the same depth, and it has to be uniform around the entire thing. So they have to be that thick, and even if it's rounded off, we have to make sure that the thickness is uniform throughout, right? So this is our typical wafer. This one's not too different from what we usually see. So we looked at the edges, the north, um, east, south, and west, and well, it's near the edges. There's no holes, so this is typical. We this is how we measure, so nothing weird here. Okay, now here is a little bit odd, right? There's some cutting right here, and this is also appropriate. There's some cutting, but they're not isolated. They don't make a hole in the middle. They still go throughout the entire wafer. There's no isolated holes, nothing's broken, and we can measure evenly across each one. So this is also appropriate. Now let's say we have a square. Well, very similar to the circle. There's nothing wrong here. It's true to what we say, and it's true to the rules. So these are three examples of different shaped wafers and what we need to do when we take measurements for them. And as long as they're all this thick and follow the rules, we're okay. Okay, here's some common mistakes that the book brings up, and it goes over their solutions. They go over the reason for these solutions and possibly the reasons for the mistakes a little bit more in depth. However, I just give you the solutions so you could get to your work a little bit quicker. So the common mistake is minority and majority carriers are impacted by the measurement, meaning that too much current is applied at the probe. So that means you're taking a measurement with the probe and you push too much current into the device, and as a result, the majority carriers and the minority characters are just changed, and their values are not true to what. And because these values are not true, it causes the resistivity to not be true. So the solution, keep measurement voltage and probes low. So 10 to 100 millivolts, right? So you're not pushing too much current. Low voltages give you true to what we think the resistivity is. That's your solution. Another common mistake, not knowing your probe spacing. Okay, so let's say you already did the measurements, right? And you got a resistivity value. You followed the rule in the first slide we just showed a moment ago, and you didn't know the spacing. You made a weird wafer or something, and you didn't keep track of the spacing. As a result, we have to take an account to what is going on right here. So your F factor is going to be these constants right here minus the spacing of the two over the average spacing between all of them. So what the average spacing was, right? So hopefully you know the spacing, the second spacing, and then the other ones are a little bit different, but it's close enough. So averaging it out and plugging that average in, the middle spacing is right here, and you just plug that in and then you bring that into the formula from before, and that's your factor for that situation. Okay, heat. Remember that your sample may be hot on one side and cold on the other. Let's say you just baked this thing and for some reason you're just getting ready to go to take a measurement. If your sample is relatively the same temperature, at least 10 ohmic centimeters or more, use the following correction factor. Okay, so I think I did this example for Google. I Googled the CT, right? So from Google, negative 0.07 near room temperature. Okay, so that's the temperature coefficient that we're going to use. And I think this is probably for silicon. A lot of the examples I use are for silicon. And the temperature in Celsius right here, minus 23, right? That's like about the one for, that's about room temp. And then the correction factor, minus 1, right? So this one is very tiny, right? But remember, we're dealing with really tiny situations. So this isn't that big of a stretch for keeping this in mind. And that's mostly everything I wanted to talk about today. Thank you so much for watching this video up to this point. This is the first time I made a video. I followed this textbook. It was a really interesting read, and I really wanted to share the information, especially in the first chapter. I might go over the fifth chapter or a couple of the other chapters that I thought were extremely useful and extremely useful for electrical engineers and some people doing analysis in clean room. Thank you so much, and please subscribe and comment the topic of video that you want next. I'll probably go over it. If there's a article that you'd like me to read and make a video out of it, I'm open ears and I'm happy to start making more videos and sharing all the information and hopefully interpreting things for you so that you could go out and do more meaningful work. So thank you so much for watching, and please subscribe if you watch this far. Thank you.